So why DMA was invented? So both programmed IO and if you consider the interpret IO, both has a one bottleneck. That is, every single byte or word of data must physically travel through the CPU. Right? Every time if I want to share the data and all, it has to pass through the CPU to give it to the memory. So the CPU has to be involved in each individual transfer. So if you are copying a 10 megabyte file from disk to the memory, that means millions of individual read a word, write a word operations, each requiring the CPU's attention. So that means the CPU is essentially acting as a middleman when it doesn't needs to be. So DMA removes this middleman entirely. So what happens is that here, while I'm transferring, let's say I'm transferring 10 megabyte of file from disk to the memory, in each of the individual, that is in each of the word, what I have to do, the CPU is involved. CPU would take each of the word, send it, store it into the memory. So from the disk it will store it in the memory. So every time in this transferring, CPU is involved. CPU would act as a middleman. So in the DMA, direct memory access, this completely we are removing the CPU here. So what is DMA module is? What the DMA module is? DMA is direct memory access module. It is a dedicated hardware controller that sits on the system bus alongside the CPU and memory, and its whole purpose is to transfer the data between the IO device and memory on its own without the CPU being involved in each word. So here what happens, you have to understand that direct memory access DMA is what? How this works is that, how it is removing the CPU is that it is actually a hardware that is going to be placed, or it is sitting in the system bus itself along with what? Alongside the CPU and memory it is placed. Okay, and its whole purpose is to transfer the data between this IO device and the memory. Without CPU being involved, it want to transfer the data between the IO devices and the memory. That is why it is sitting in the system bus alongside the CPU and the memory, and it has its own internal register to keep track of the job it's been given, and it can take control of the bus to move data, essentially impersonating the CPU for the duration of the transfer. So here what happens is that these DMA has some internal registers within them. Now these DMA has the internal registers within them, and that internal registers can be used to keep track of the job what it is being doing here. And it can control the what it can do is that it can take the control of the bus to move the data, right? So it is present in the system bus. In order to move the data, the DMA, when it wants to move the data, it will take control of that bus and moves the data. And this DMA also contains some internal registers between them, inside them, to keep track of its job. What the CPU tells the DMA, when the CPU wants a block of data to transfer, it issues that block of data one-time command to the DMA, and the DMA module walks away. The command contains exactly 4 pieces of information: whether this is a read or write operation, the address of the IO device involved, the starting memory address where the data should be read from or returned to, and the number of words that you have to transfer. So when the CPU is telling DMA to transfer something, what are the information? So that means the CPU would send one block comment. Okay, that command would that it will give to the DMA, and DMA would walk away with that command. So in that command it would include lot of things. The 4 things it include is that whether it is a read or write operation. Now what is the IO device's address? Now from which address in the memory I have to read or write that data, and number of data which is basically transferred, number of words that is basically transferred here. This much information would be covered here. So we have to understand direct memory access, there is no involvement of CPU here. Here usually in every time the CPU would act as a middleman, but in here CPU is entirely, basically you are removing the CPU. In here this direct memory access is actually a dedicated hardware that is sitting between the memory and the CPU. Now that main whole purpose is to transfer the data without the involvement of CPU between the IO devices and the memory. So they have dedicated data registers within them that can keep track of this job. The next point that you have to remember is that it can also, whenever it wants to, because it is present in the system bus along with the CPU and the memory, when it wants to transfer a data, what it will do, it would take that data and move that data through the data bus. Okay, now you have to understand why a CPU would give one block of the command to the DMA, and DMA would walk away with that command. That command would include whether you have to do read or write operation, whether you have to fetch from which address in the IO device, from which address you have to fetch that data, the starting memory in which you have to read or write, memory address, and the number of words that you're going to transfer. All of these things has to be involved. Now you have to understand this concept of cycle stealing. That is, DMA now is taking over, so it has to transfer one word at a time. So directly between the IO device and the memory, but bypassing the CPU entirely. But here what happens is that there is a physical constraint. Both the CPU and DMA is both sharing what? The same system bus. So here what happens is that through the system bus itself, the DMA has to share the information, transfer the data. CPU also is using the system bus. So the problem here arises that only one of them, whether it be CPU or DMA, only one of them can choose the bus at one time. So this DMA resolved this technique using the concept of cycle stealing. So DMA watches the bus and grab it during the moment CPU is using it. Typically when CPU's instruction cycle, the DMA steals one bus cycle and transfer one word of data, then release the bus. So here what happened, when the CPU is not using, at that time, that is, it would take one CPU's one bus cycle and it would steal that. That is why it is called a cycle stealing. It would steal that one bus cycle and transfer one word of data, and then it will release that bus. So the CPU may slow down slightly because occasionally it finds the bus occupied, but it never stops completely. CPU may slightly would slow down a little bit because it sees that the bus is occupied, but it would never stop completely. Meanwhile, the DMA is steadily chipping away at the transfer, one stolen cycle at a time, until the entire block is done. So here what happens, cycle stealing is happening. One cycle of the CPU we will basically steal. Okay, no much difference it will cause. When the last word the block has been transferred, the DMA module send a single interpret signal to the CPU. The CPU come back and use that data. So the CPU was interpreted just one at the very end rather than once per word. So in the interpret driven, per word you are going to send the interpret. Instead of doing that, after every data has transferred, then only the interpret signal is given. So by the time the CPU receives, all the data is already sitting in the memory and it is ready to use, right? So when the CPU is resuming here, what happened, it will send interpret to the CPU. So what happened, the CPU was interpreted only just once, and by that time the CPU is resuming, all the data is present in the memory itself and it is ready to use there. That is the main advantages of the DMA. You don't need to do multiple interpret, only one interpret signal would be sent here. And the concept of cycle stealing you have to remember, and what are the information which is present in that command, that you have to know. And you have to know that there are data registers, you have to know the location of the DMA and how it takes control of this data bus. All these things you have to know. And why do we need DMA? All these things are the most important things that you have to understand. Now when the payoff here is that consider transferring 10,000 words from the disk. With interpret driven IO, the CPU is interpreted 10,000 times because only one time one word would send. So executing dozens of instructions each time. With DMA, the CPU is interpreted only exactly once. The DMA would handle the transferring of all these 10,000 words transfers independently, and this would free the CPU to run the other program and handle the other task or symbol execute more useful work by that time. Right, so for large data transfer, disk read, network packet, video buffer, DMA is not just faster, its transformativity more efficiently. Right, so for large data control, it's not just faster, it transformatively it's more efficient. When you're dealing with very large data and all, CPU cannot simply every time it has to deal with this interpret. So in order to prevent this, which is more efficient in the case of large data, in the case when you are dealing with large data, more suitable would be what? So the DMA is much more faster and much more efficient in the case of larger data. Let's say the DMA block, we have the control logic in the DMA block. And address register, data register, and data com. We have to know the data, how many data is there, how many number of words is there. Okay, so that part we have to know. Address line part is the, because address of where you have to go put it in, that is important. And the data, what data, so data lines is also needed, data register is also needed, data count is also needed. And also what is required, address register is required. Address register, what it will do, it would for the address line. Now the DMA, it will request to the DMA, and DMA would finally, after sending, the DMA can send acknowledge from the DMA and interpret also. Read and write, whatever it has to do, that would come, that signals has to come to the DMA itself. So when we are trying to draw here the DMA's block diagram, you have to understand that in DMA's block diagram, you have to understand what are the parts. The main part is the control logic. So the main part you have to draw first, that is what the control logic. So first we have the control logic, that is the main part. Then we have the data register, data count, and the address line. Okay, this is my address part. Okay, this is my address part. This is connected to what, my address lines. Okay, this is connected to my address lines. Now we have to understand there is a data count, there is a connection here, and then data count is the, and data register is the, all these belongs to what, data lines. Okay, now acknowledge, interpret and all can acknowledge, if you take acknowledge, interpret, all this can come from the control logic. But to read something you have to give it to here, to write something you have to give it to the control logic, right? So, and if I want to request something to DMA, that also I have to give to the control logic. There are different registers. So this is how the block diagram, whenever you are learning DMA, whenever the question comes about DMA, try to draw this block diagram. Okay, that is the most important thing here, drawing this diagram. This can even give us the full marks. So that is one important thing that you have to understand. Draw this block diagram. Data count, data register, address line is the, data line is the. Then in the main control logic, we have the acknowledgement from the DMA, interpret from the DMA. Then you have the read, write, all this to the control logic, and you also have what, request to the DMA. Okay, in request is also given to the DMA, read, write, all these things are given to the DMA itself. Fine. Now you have to understand the DMA and interpret breakpoints during the execution cycle. Here what happens is that these are the different processors cycle. Now you are fetching the instruction, decoding the instruction, fetching the operands and executing the instructions. So the DMA breakpoint is that there is interpret breakpoint. Interpret breakpoint only would come after you have finished the complete things. Only interpret breakpoint can come. But DMA breakpoint can come before you have started fetching, after the decoding part, and after the executing of an instruction. So these are the times in which DMA breakpoints can come. But interpret can come only after that instruction has been finished. The complete instruction has finished, only interpret breakpoint can occur. You have to understand. These are the different processor cycle. The time is given to us. Now, fetch instruction is a decode instruction, is a fetch operand, execute the instruction, a store result. This is how the execution of the instruction is occurring. Now, during the execution, after the complete execution of the instruction, only interpret occur in the interpret IO. Okay, then we will process that interpret. But the DMA breakpoints can happen before the fetch, after you have decoded the instruction, then also it can happen, and after you have executed the instruction, then can also happen. So these are the places where the interpret, breakpoints can occur. So you have to remember the places in which interpret breakpoints can occur. This is another important thing. So here we are talking about the most important points here. So you have to learn these important diagrams. As I told you, this important diagram about the DMA, why do we need DMA, maybe for 3 mark or any mark it can ask. So you have to remember that. Okay, So you have to understand that the breakpoints would be what after you have decoded, or maybe before the fetching the instruction part, or after execute the instruction would be the breakpoints would occur here. So let's understand the concept of cycle stealing. I told you the cycle stealing happens when you are taking the one cycle you are stealing from the CPU. One CPU cycle you are basically stealing for transferring the data. The key insight here that CPU does not use the system bus in every single clock cycle. It does not use the system bus. The instruction cycle, we know it has fetch, decode, execute and write back stage. So and during some of these phases like decode phase and all, decoding and all, we does not read the bus site. Bus is not in, no transferring is happening here. So the DMA module watches for these ideal gaps where the CPU is sitting idle. The moment it finds the CPU is about to need the bus for the next phase, the DMA quickly requests it and transfer exactly one of the, so it would see where this ideal part is there. Like, you know, when an instruction has to execute, fetch, decode, execute and write back, these stages are there, but in all of the stages the buses is not required, the system buses are not required, like the decoding phase. So the DMA would look in that bus, that part, as you can see the breakpoint, like after the decode. So before going to the next, what happens is that at that the DMA would quickly request that and transfer exactly one word of data in the, then releases the bus before the CPU even notice. This is fundamentally different from an interpret, because in interpret the CPU saves its entire context and jump to a different routine, that is interpret service routine, and complete it and restore the context that it was done, then will continue the instruction. But in cycle stealing, the CPU simply waits only one extra clock cycle at a bus boundary. There is no context save, there is no jump, there is no restoring here. CPU receives from exactly the same point with zero awareness. CPU would not even notice this. That is the thing. Only one clock cycle it becomes less. The CPU would has to wait only one extra clock cycle. The CPU receives from the exact point with the zero awareness about what has happened here. The only side effect is that the processor runs slightly slower overall because it occasionally waits an extra cycle. The only problem is that like little time it would basically wait. But this is actually better than interpret driven IO, because in interpret driven IO what happens is that it has to wait for the whole cycle. That means it has to save the context and then it has to do the routine, ISR routine, and it has to again restore the things that was there. So it is basically a problem. But here only one or small clock cycle, one clock cycle delay would only happen here when you're transferring one word of data. So what happened is that the CPU would not even notice that. That is the main thing. So here cycle stealing is more efficient. So the time where the CPU doesn't require the bus, so that time when the CPU is sitting idle, like after the decoding part and or before taking that, that would be a DMA breakpoint, or after executing instruction, it would at that time execution part there is no system bus needed. So that is an idle part. So before going to the next stage, it would occupy that. So these are the different DMA breakpoints. So cycle stealing, if you wanted to say, you can say it like this. So there are three main DMA configurations, okay, so that you have to understand. These are the different three main DMA configurations. As you can see, single bus detached DMA is them, and a single bus integrated DMA IO is them, and the next is this. These are the three different configurations in which DMA can be there. Okay, so let's see the first configuration. So we are going to see now each of this configuration, each of this DMA configurations in detail. Then after that, what we have, but each of these configurations, that only we have to learn it clearly right now. So if you look at each of the configuration, the first thing is the configuration number 1. In configuration number 1, it's a simple to build but is the most inefficient to run. Here all components, CPU, DMA, memory and IO devices are sharing the one bus. So when DMA is transferring a word, it first read it from the IO device which is onto the bus itself. That is IO first, it reads it from the IO device onto the bus, onto its own internal buffer, then writes it from its buffer out to the memory. So bus cycle 2. So every single word costs 2 full bus cycle. The bus is occupied twice as long as it needs to be, and the CPU is frozen out twice per word. So the textbook correctly called this as clearly inefficient. So here what happens is that the CPU, the DMA, the IO device, the processor, all the IO devices, the processor, DMA and memory, all of them are present in a single bus. So IO device has to give the data first to the DMA, so that it has to go to its internal buffer first to the system bus itself, and that data it has to take from its internal buffer. So 2 times what happened is that then it has to go to the memory. So 2 times, so one time the IO is basically giving it to the data bus. So from that internal buffer it has to take, DMA has to take the data, and the other time it has to give to the memory. So again you have to use the system bus. So the processor becomes 2 times slower because 2 cycles are being here wasted in this case. So here what happens is that when DMA transfer it words, it has to first read it from the IO. So first bus cycle 1 means what? Bus cycle 1 means it has to the data which is needed from the IO device, first it would put in the system bus, that would be stored in the internal buffer. Then from there I have to take and write it from its buffer, from its internal buffer I have to put it, and from there I have to put in the system bus, then I have to give it to the memory. So 2 times the bus cycle is used in the first configuration. So since it's used 2 times, how many times has become? Okay, since it becomes 2 times we are using the bus, so what happens is that it becomes very difficult because the processor becomes 2 times slower. This is a problem. It is clearly inefficient. We cannot use this method, though it is simple to design, simple to basically build, okay, but it is inefficient to run this. The next is a single bus integrated DMA IO. That means in DMA the IO would be integrated. As you can see, there would be one single bus, the processor, DMA and memory would be connected to it, and in DMA would have this integrated IO. As you can see, DMA has this integrated IO. So here what happens is that it would fix the issue of this double cycle problem which was here by eliminating the DMA's internal buffer as a stopping point. So DMA controller is built directly into the device, and the disk controller, the network controller, etc. DMA controller is built directly into the device. So when a transfer happens, the data goes straight from the device onto the bus and into the memory. That means from the device the data can go directly to the memory because the DMA controller is built in this device itself. That means in this IO devices itself we have built the DMA controller. DMA controller can be each of the device, network card controller, disk controller. So the DMA controller is built with this device itself. So transfer can happen directly from the device to the memory in a single bus. So the halves the bus usage compared to the configuration. Here there were 2 cycles, but here only 1 cycle is used. So it is the most practical embedded DMA system work. So this is the most practical, I would say, because here in the device itself we have embedded, right? The device has this DMA controller. Each device is basically embedded with this DMA controller, is built with this directly with this device. So what happens is that it eliminates the issue of having multiple, that is 2 cycle issue that it has. It actually removes that issue of having 2 cycles. That issue basically is removed, and what happens is that because of that the device can directly send the data to the memory in 1 cycle, in 1 bus cycle only. Okay, this is about the single bus but integrated DMA IO. This is detached DMA. DMA and IO is detached. The single bus detached IO is my first configuration. My second configuration is single bus but integrated DMA IO. Fine. Next we have another where there is basically 2 buses. Here what happened is that this is the most powerful approach and the one which is used in the modern computers. There are 2 separate buses. The high-speed system bus used only the CPU, DMA and the memory. This is a high-speed system bus. Then there is another bus which is IO bus, which is dedicated to the peripheral device. The IO devices talk to the DMA over this IO buses, and the DMA talk to the memory over the system bus. So the IO devices, there is a separate bus for the IO buses. So IO devices devices can talk to the DMA through this IO bus, and DMA can talk to the memory using the system bus. So the most modern computers and all use this approach. This is the most powerful approach. This is a practical approach. This is the most inefficient approach. So here there is an IO bus, and most of the devices connected to this IO bus. Now IO bus can send the data to the DMA using this IO bus here. IO devices can send the data to the DMA using this IO bus here, and DMA can communicate with the memory using this system bus. Okay, I hope you have understood. So this is about the different configurations. Okay, so this is about our one important topic. I hope it's clear.